right? So in Calculus 1, you learn that critical points are places where the first derivative is equal to 0. And once you find the critical points, you kind of have a list of places where relative maximums and minimums could exist. And to determine whether it was a maximum or a minimum, most of the time, not all the time, but most of the time, you could do what we call the second derivative test, which means you take the second derivative at that point, you figure out if the function's concave up or concave down, determine if it's a maximum or a minimum. But sometimes that failed, and sometimes if your second derivative was equal to 0, that means there's no concavity, but it could still actually be a maximum or a minimum or neither, and you just don't know. The couple of examples I could show you for that are like, if you have the function y equals x cubed, the critical point is right there at the origin. It's where the derivative is equal to 0. But if we tried the second derivative test, we'd find that the second derivative is equal to 0 at the origin. And this is a case where this is neither a maximum nor a minimum. But if I have the function x to the 4th power, then again, I've got a critical point at the origin. But if I try the second derivative test, I get 0. And even though the concavity is 0 there, the second derivative is 0, this is still a minimum of the function. And likewise, if I had negative x to the 4th, that's another place where the second derivative is equal to 0, but that's actually a maximum. And so getting a second derivative equal to 0 doesn't tell you anything about the nature of that critical point.
Like same thing, when the second derivative test doesn't work, we go back to the first derivative test.
Yeah, what you could do if the second derivative test doesn't work is you could sample points, not just to the left and just to the right of the critical point, and determine whether you're increasing or decreasing using the first derivative, yeah. And then on the second page of those notes, I have this, and it just tells you that if you have a multivariable function of like 2 variables, for example, then what we would call the critical points are the places where both of the partial derivatives of that function are equal to 0 simultaneously. So if just one partial derivative is equal to 0, that's not a critical point. But if both are simultaneously equal to 0, then that's what we call a critical point. If you had a function of 3 variables, then all 3 partial derivatives would have to be equal to 0. If you had a function of 4 variables, all 4 partial derivatives would have to be equal to 0 to have a critical point. So just like with single variable functions, as long as you have a smooth surface, then these critical points, it's going to be like a list of all the places where you could have a relative maximum or a relative minimum. The extra weird thing that we get with multivariable functions is something called a saddle point. So saddle points don't happen for single variable functions, but GeoGebra. There we go. But for multivariable functions, I could type in something like z equals x squared minus y squared. And then that's sort of like a potato chip or a saddle shape. And so right here at the origin, I've got a critical point. So both the x partial and the y partial are equal to 0 at the origin. But that is neither a maximum nor a minimum of my function. And so that's what we call a saddle point. Again, that's brand new for multivariable functions. This could still happen with functions of 3 variables or 4 variables. We wouldn't use a surface to represent those functions, but again, if you have a situation where it's neither a maximum nor a minimum, but you still have a critical point, it could be one of these what we call saddle points. So, I'm trying to recap this very briefly because I know I'm going to say this all again after spring break. If you want to distinguish between these, this is the multivariable equivalent of the second derivative test. Okay? So, if you have a multivariable function, it's not just take the second derivative, it's like take the second partial derivative with respect to what? And if we have 2 variables, then we have to consider the second partial with respect to x and the second partial with respect to y, and the mixed partial with respect to x and y. We talked a little bit earlier in this semester about determinants of a matrix. And so I can actually say this to you guys, whereas I would skip over this, talking to my business calculus class. If I define a matrix like this, where this is the second partial with respect to x, and this is the second partial with respect to y, and this is the partial with respect to x and y, and this is the partial with respect to y and x, and then I take the determinant of this matrix. The determinant of the matrix is, top left times bottom right minus bottom left times top right. And so that is what's going on here with this formula. This is just taking the determinant of what we call the Hessian matrix. So the matrix with all the entries being the second partial derivatives of a function of two variables. This is called a Hessian matrix, named after a mathematician named Hess. So anyways, what we do to determine the critical points, or how to characterize the critical points, we take the determinant of the Hessian matrix, and then we say, well, if this is greater than 0, and the second partial with respect to x is less than 0, excuse me, then my function has a local maximum. Again, if this is determinant is greater than 0, and the second partial is greater than 0, then we have a local minimum. If this determinant is less than 0, we have a saddle point. And if this determinant is equal to 0, then it's like the second derivative test has failed. We can't tell if it's a maximum, we can't tell if it's a minimum, we don't know if it's a saddle point. And it could be neither. It could be neither of all of those, right? It could be like the x cubed case where it just goes flat and then continues up and it's not really anything. The next thing is called the method of Lagrange multipliers. And the method of Lagrange multipliers is something like this, right? We want to maximize some variable, like profit, subject to some constraints. And so what this means is, like, if I have profit as a function of x and y and z, I want to maximize that. And so initially we think, okay, we just need to find the critical points and then characterize the critical points, right, using the procedure we just talked about. But what if there exists some relation between x, y, and z? Like, what if I have to have that x squared plus y squared minus z squared is equal to 0, right? What if there is some relation between the independent variables that I cannot violate, right? So if I only considered this function, then I'd be in trouble, because probably the maximum that I'm figuring out of this function does not necessarily respect my relation. And so the method of Lagrange multipliers is going to be a way where we can say, what are the optimum points, or the critical points of my multivariable function subject to some specific constraint relations between my independent variables. And so, again, we'll get back to that after spring break. What I wanted to talk about today, as much as possible, is to try to get started on the foundations of our group project. So we're going to start on this group project after spring break, and I'm going to try to do as much as I can to set you up for success for that. We teach this in our algebra class at Midland College, so I hope that you guys have seen this before, and I hope that this is going to be short work here. But if you're asked to solve the following system of equations, which is x plus 2y equals 8, and 3x plus 4y equal 9, the way that I would solve this is I would take the first equation here and multiply the whole thing times -2, yeah. And then I would get -2x minus 4y equals -16. And then I'll just add these two equations. I add the second line to the third line, and I would get x plus 0y equals what? -7. And if I take this x equals -7, and let's say I plug this back into my original equation right here, then I would get -7 plus 2y equals 8. And so that means y is equal to what? Yeah, 15 halves. Cool. So that's what we call solving by elimination. We can solve a system of linear equations by elimination like this. And these were linear equations because we don't have any x squared, we don't have any y squared, we don't have any x times y, we don't have any sine function or anything crazy like this. They're just linear equations. So if we have a system of linear equations we can solve with elimination. The next step to make this a little bit more sophisticated is we're going to start by writing out an augmented matrix. And what an augmented matrix is you take your system of equations and then we're going to write just the coefficients of the variables in order x, y, and then the constant after the equal sign. And then again we have 3x, 4y equals 9. So this little 2 by 3 matrix is what we call my augmented matrix. And if you remember what these numbers represent, you can do the same kinds of operations to the rows of this matrix that you would normally do to one of the equations in your system of equations. Like what we can do is we can still say, let me take the first row and multiply it by -2. So if I take the first row and multiply it by -2, then this is my new augmented matrix. I can still say, let me add the first row to the second row. And if I take the second row plus the first row, then I would get something like this. I can still do something like, I can still swap the order of the rows if I wanted to. Like let's just say I want to interchange the order of rows 1 and 2. Then I could still write 1, 0, -7, -2, -4, -16. Because this is, again, each row just represents an equation in my system of equations. It doesn't matter which order you write the equations in. So you can interchange rows as you want. And then what I could do is I could add 2 times row 1 to row 2, and I would have 1, 0, -7, and then 0, -4, and 2 times -7 plus -16 is going to be -30. And then I could take the second row and divide the second row by -4, and -30 divided by -4 would be 15 halves. And so again, every step of the way, these rows of the matrix represented equations in my system of equations, where the numbers were the coefficients of my variables until the last column, and the last column was the constants on the other side of the equal sign. And I can just reconstruct my system of equations And now what this matrix is telling me is 1x plus 0y equals -7, and 0x plus 1y equals 15 halves. And so that's the same solution we found earlier, but this time we wrote an augmented matrix, and then we manipulated the augmented matrix using like these allowed row operations. So what you're allowed to do, you're allowed to interchange rows as much as you want. You can swap the order of the rows in your augmented matrix. You can add rows and subtract rows from each other. And you can also multiply any rows by any constant. You can multiply by -1, you can multiply by 5, and so on. But the goal here, the goal of taking an augmented matrix and then doing what we call Gaussian elimination, named after Carl Gauss. The goal here is that elimination. The goal here is that we want to have ones on what we call the diagonal of the matrix. So the first row, first column is 1, the second row, second column is 1. If this were a 3x4 matrix, then the third row, third column should be a 1. And we also want to have zeros as the entries above and below the diagonal in order to have it what we call like fully reduced. And once we get into that point, then we can just read off what the values of the variables should be. So an augmented matrix is just where you take the coefficients of the variables and then the constant on the other side of the equal sign. The goal of Gaussian elimination is that you end up with some matrix that has ones on the diagonal, zeros above and below the diagonal, and then you get the values of your variables in the last column, right? And then the allowed row operations, like we talked about, is you can swap rows, you can add or subtract rows, and you can multiply rows by a scalar. And that's important. You can't multiply rows by each other. You can only multiply rows by a scalar. Right? That's a common mistake that I see in my algebra classes as people try to multiply row 1 times row 2. That does not work, because that wouldn't work for just doing, ordinary elimination on your system of equations, so it doesn't work for this case. One question you might ask is, can I swap the columns? And so let's think about what that would mean really quick if I just have some, system of equations like this. If I wanted to swap the columns, what that's essentially doing, let me write the augmented matrix really quick. If I wanted to swap columns 1 and 2, then I would be writing 3, 5, 2, 3, 5, 7. What I've done now is I've changed the order in which my variables are represented. Right now, this is the first column representing x and the second column representing y. Now, the first column represents y and the second column represents x. So the answer to this, can you swap columns, is yes, you can, but you have to keep track of the order that your variables were in, right? You can't do this and then expect to read off your variables x, y, z. Now you've got to remember that your variables are in a different order, y, x, z, when you read out your solution. But that is possible. Let's do a little real-life example.
Good question. For the augmented matrix, was it possible after the elimination part to find the inverse matrix?
Yeah. We'll talk about inverse matrices here in a moment. Yep. Yeah. If we get to it today, we'll talk about that, and if not, then we'll talk about it tomorrow. But we will eventually get to inverse matrices.
So basically, like multiply the last row, the last column by the inverse to get the identity, right?
Yes. Okay, so what if you were like really into like fitness and nutrition and stuff, and you wanted to track your macronutrients? And so you want to know exactly how many carbohydrates and how many proteins and how many fats you're eating every day. But you're also really lazy and you just want to drink smoothies for every meal. So you want to design a smoothie that has exactly the ratio of carbohydrates, proteins, and fats that you want. And let's suppose that the only ingredients that you have access to are oats and peas and coconut. So with these three ingredients, oats, peas, and coconuts, you want to make a smoothie that has exactly 52 carbs, 35 grams of protein, and 23 grams of fat. How do you choose how much oats, how much peas, and how much coconuts you want to add to your smoothie in order to get exactly these macronutrients from your smoothie when you drink it? In other words, how do you determine that recipe? Step number one is we're going to set up a little system of equations where we say X is going to be my variable representing grams of oats in my smoothie. Y is going to be my variable representing grams of peas in my smoothie. And Z is a variable that represents grams of coconut that I add to my smoothie. And to get an intuition for the problem, oats are primarily carbs. And so if I make a mixture of oats, peas, and coconuts and I'm a little bit low on carbs, I should add more oats to the mixture to boost the carb count. Peas are particularly high in protein, and so if I have a mixture of my oats and peas and coconut, and it's low in protein, then I should add more peas to boost the protein, count. And then coconut is higher in fat. So if I make a mixture and it's lower in fat than I want to boost the fat content, then I should be adding more coconut. And then eventually we'll settle out into a nice ratio of exactly these macros that we want. But setting this up, I know for every 10 grams of oats, there's 7 carbohydrates. And so if I write 7 over 10 x, this represents the carbohydrates that I'm getting from the oats. Then I know for every 10 grams of peas, I get 3 carbohydrates. So if I write 3 over 10 y, that represents the carbohydrates I'm getting from my peas. And then if I write 4 over 10 z, that represents the number of carbohydrates I'm getting from my coconut. So carbs from oats, peas, and coconuts, if I add them all together, I want 52 total carbs. Okay? So that is my carbohydrate equation. For my protein equation, I have to say, well, for every gram of oats, I'm getting 2/10 protein. For every gram of peas, I'm getting 6/10 protein. And for every gram of coconut, I'm getting 1/10 protein. Altogether, when I add up my protein from my oats, peas, and coconuts, I want a total of 35 grams protein. So that's my protein equation. And then lastly, for my fat equation, I'm going to write 1/10 x plus 1/10 y plus 5/10 z equals 23, because I want 23 grams of fat total. So now I've got a system of 3 linear equations with 3 unknown variables. And now I can solve this using Gaussian elimination. The first step is going to be setting up my augmented matrix. And so this augmented matrix is going to read 7, 3, 4, 520, because I'm going to multiply the whole equation by 10, just so I have integer numbers to deal with. And then I'm going to have 2, 6, 1, 350, and then 1, 1, 5, 230. Okay. Let's start out by subtracting 3 times my second equation from my first equation, right? I've had the 7, and I want it to be a 1, because I want 1s on my diagonal, right? The goal here is 1, 1, 1, and then 0s below the diagonal and 0s above the diagonal. Then I could read off my answer. So to make this 7 into a 1, I'm going to subtract 3 times the second row from the first row. So 7 minus 3 times 2 is 1. 3 minus 3 times 6 is negative 15. 4 minus 3 times 1 is 1. And then 520 minus 3 times 350 is
530.
It should be negative.
Yeah, negative 530.
Does everybody agree?
Oh, negative.
Okay. I'm trusting you guys because I'm not going to do that in my head. So that would be my new first row with the 1 there. I want this 2 in the second row to be a 0 because it's below the diagonal. And so I think I'm going to subtract 2 times the third row from the second row. So then I have 2 minus 2 times 1 is 0. 6 minus 2 times 1 is 4. 1 minus 2 times 5 is negative 9. And 350 minus 2 times 230 is negative what? Negative 110. Thank you. And then for my third row, I want that leading 1 to be a 0. And so I think what I'll do is I'm going to take this third row and subtract my new first row, which is allowed. So I can do 1 minus 1 is 0. 1 minus negative 15 is going to be 16. 5 minus 1 is 4. And then 230 minus negative 530 is 760. Okay. So I'm inching closer to my ideal augmented matrix because now I've got 1, 0, 0. The next thing I'm going to focus on is making this 4 into a 1. So to make this 4 into a 1, it's going to be a little bit tricky. I think the first thing I'm going to do is multiply the second row times 4. Well, no, that doesn't work. Because that'll ruin my first column if I do that.
What if we divide the last row by 4 and then we can't divide by
You can divide.
like a row within a row?
No, you can't divide row by row.
Yeah, so
You can divide by a scalar. Trying to think if I've got any. Let me take the last row and divide it by 4, just because I think that's factoring out a greatest common factor. That's got to make a little bit of progress. And so instead of 16, I'll have a 4. Instead of a 4, I'll have a 1. And instead of 760, that would be 190. Okay. again, the difficult part here is I'm trying to make this into a 1. And ideally I would like to do this without having to resort to fractions, but that just might be the way that we have to go for this. It's the old fractions. Okay, so then I'm going to go ahead and divide the second row by 4, and we're going to have to deal with some nasty fractions. So dividing the second row by 4 makes this a 1. This is going to be negative 9 over 4. And then 110 divided by 4 would be 55 halves.
No, 27. Oh, yeah.
Yeah. And then, again, I hate dealing with fractions whenever I do this, but it seems like it's the only way to proceed. What I'm going to do is now I'm going to take the third row and subtract 4 times the second row. I probably should have done that before I divided the second row by 4, but take the third row and then subtract 4 times the second row. So here is you've probably realized by now that there's more than one correct way to do this, and that some of the correct ways to do this are easier than other correct ways to do this. So I'm probably not being the most efficient that I could be, but so 1 minus negative 9 would be 10. And then 190 minus negative 110 would be 300, right? Okay. Then I can just divide the third row by 10, and then I have 1 and 30. That's pretty nice, at least. And so we're getting closer, right? I've got 1s on the diagonal now. I've got 0s below the diagonal. The last step is to get 0s above the diagonal. So let's focus now on this negative 9/4. Let's try to make that into a 0. And to get that into a 0, I have to add the third row to the second row 9/4 times, right? Think about multiplying the third row times 9/4 and then adding it to the second row. So that means negative 9/4 plus 9/4 times 1 is 0, like we want. But that means I have to do negative 55 halves plus 30 times 9 over 4.
I think it's like
So that would be 270 halves. What's 270 minus 55? 235 halves. Did I make a mistake here?
I think it's 215.
215, yeah.
It's 215, sorry.
Yeah.
Okay.
Yeah.
You multiply it by 9 over 4, not 9 over 2.
Yeah.
So it'll be 270 over 4. And
Yeah, 270 over 4 and then 215 over 4.
270 over 4? Okay. So 270 over 4 is 135 over 2. And then 135 minus 55 is 80, which is 40. Okay, I knew this had a nice answer. Okay. Now, I want this 1 in my previous matrix. I want that 1 to be a 0. So I'm going to subtract the third row from the first row. Okay? So 1 minus 0 is 1. Negative 15 minus 0 is still negative 15. 1 minus 1 is 0. But I have to do negative 530 minus 30, which gives me negative 560. And we are just so close. One more step. And now what I need to do is add 15 times the second row to the first row. So the second row times 15, well, so 1 plus 15 times 0 is 1. Negative 15 plus 15 times 1 is 15. 0 plus 15 times 0 is 0. Sorry. Yeah. That should be also a 0. Negative 15 plus 15 times 1 is 0. Negative 560 plus 15 times 40 is the last math problem that we have to do.
I think it's 1,400.
So 15 times 40 should be 600. 600 should be okay. Plus, okay, there we go. Ha, 40. So, what a nice answer. What this means for us is 1x plus 0y plus 0z equals 40. 0x plus 1y plus 0z equals 40. 0x plus 0y plus 1z equals 30. So that means x is 40, y is 40, z is 30. Which means what's the recipe for our smoothie? It is 40 grams of oats plus 40 grams of peas plus 30 grams of coconuts gives you exactly the macronutrient mixture that you want for your smoothie.
So,
And now you can just,
so this would be the logic of
make a huge batch of that and live off of it for 6 months or whatever, and you'd be sure that you're hitting exactly your macros.
So this is the logic of the project, correct?
Sorry?
This is the logic of the project.
This is the project's going to be a little bit more involved in this. Yeah, this is just one little piece of the foundations that you need to know.
For the grams of protein and fat and carbs of each of them.
No, I made that up. I don't actually know. I didn't actually use real numbers for the nutritional values of oats and peas and coconuts. I was just making numbers up for the. Yeah.
Maybe.
So.
I don't know.
No, those are just wild guesses, and so if you made that exact recipe, it probably won't give you those macros. But this is kind of like a real life problem because there are companies that make like meal replacement shakes, like Pediasure and Ensure, and Soylent, and other things, and so they have people like dietitians or nutritionists or mathematicians or whatever that sit there and solve these types of problems, but it's just a system of linear equations with certain unknowns and certain targets they want to hit. And so this is how you solve it. Okay, so let me show you if I can find it. So what I have is a little code that I wrote in Microsoft Excel. If you didn't know, you can code in Excel. You just go to Developer, and then you go to Visual Basic, and then you can write a little thing. So this is my personal algorithm for doing Gaussian elimination on matrices, and it does exactly what we did, the same exact process, only it does it automatically, because I don't want to do that by hand every time. Right, that's kind of a long, boring math problem. And, okay, where were we at in my notes? The augmented matrix we started out with was 7, 3, 4. $520, 261, 350, 115, 230. Let's see if we get the same results whenever I hit the button on my little Excel spreadsheet right here. Yeah, so this just quickly, a lot faster than we did, row reduces the matrix to get 40, 40, 30. And this is the whole idea. Because, you know, you and I can solve systems of equations with the old like elimination method where you multiply the equations by some number and you add them together and whatever. But like you end up with a lot of extra symbols, and it's not easy to tell a computer how to do this. But with what we just talked about with the Gaussian elimination of the augmented matrix, you can just type in an augmented matrix in Excel, and then you can, if you want to, I'll email you this code. You can write computer code that step by step, line by line, tells them exactly what to do to each row in the matrix under what conditions until you finish row reducing your matrix. And so in practice, people don't solve those by hand. In practice, those problems are just so freaking boring that nobody like sits down at their desk and by hand solves those. Instead, what you do is you teach a computer how to do that, and then you can make a matrix as large as you want, like this monster 11 by 11 matrix, which would take me all day to row reduce. And then, you know, once you've programmed it once, then you've solved the problem forever. You never have to return to it. And so kind of what we're going to be doing for your group project is not exactly this, but for your group project, I'm going to give you a certain type of problem, a certain type of optimization problem. You're going to need to use Lagrange multipliers. But what I would like you to do with your project is to write a code, and it could be in MATLAB, it could be in Visual Basic, it could be in Python. You just have to decide with your group what you want to write it in. But I want you to like write this MATLAB code not only to solve a specific problem, but I want you to write a code that solves every kind of problem. Kind of like if I type in any numbers into this matrix, I can always row reduce it using the same program. You're going to write a program that solves a general type of problem like that. We've got 2 minutes left, but I think I can finish telling you about what I want to tell you about. The last thing I'll say is this. If you go in Microsoft Excel, and what's the magic thing to type in? 1.005. In Microsoft Excel, if you type in equals 1.005 minus 1, what should be the answer? 0.005, okay? Okay, it looks like you got it right. Looks to be correct. Looks like that probably should work, you know. But if I increase the precision and tell Microsoft Excel to give me more and more digits, then it breaks. And Excel's like, no, 1.005 minus 1 is actually 0.0049999999999. You know, it's not exactly 0.005, which is a little bit dumb. You would hope that it would be exact, and it's just not. So the reason this pops up is because in Microsoft Excel, and this is the same for Python too, is numbers are stored as a data type called double precision floating point variables. So if you want to Google search that, you can learn all the computer science behind double precision floating point variables. But the idea is this, is that in your computer memory, everything is stored as bits. It's either a 0 or a 1. So how do you store numbers using just strings of bits? And the answer is you can only have a certain precision with the numbers that you have. And there's only a finite number of numbers you could store with a finite number of bits. So you can store a whole lot of numbers, but the number 0.005 does not belong to the set of numbers you can represent using this scheme of storing numbers in computer memory. So instead, since we can't have 0.005, Excel just gives us the number that's closest to it in the set of all numbers that you can store using this scheme called double precision floating point. what this ends up doing for really, really large calculations is it introduces a little bit of error that we call round-off error into our calculations. So anytime you have a computer do this massive calculation, there's a chance that it's going to be tainted with what we call round-off error. And so one of the consideration that like applied mathematicians have to take into account is like in your problem that you're solving, are you accidentally introducing too much round-off error to where your answer becomes garbage? And this kind of thing shows up a lot in like what we call chaotic dynamical systems. Predicting the weather is a matter of chaotic dynamical systems. So that, I don't know if I've said this to you before, but anybody who thinks they can predict the weather more than like 5 days in advance is just absolutely wrong. You know, I think it's funny because on my weather app, they'll be like, here's the 5-day forecast. If you want more than 5 days, subscribe to our premium service and pay like $2 a month for the 10-day forecast or whatever. But, you know, after the first 5 days, the predictions are garbage. And the reason is because calculating these big, big, big dynamical systems that are subject to chaos, like the weather is subject to chaos, introduces so much round-off error that you can't make a solid prediction. And even if you could completely eliminate round-off error, specifically in the case of weather, the tiny, tiny, tiny differences in our measurements of pressure and temperature and wind speed and wind direction and all the measurements that those predictions are based off of, those contain errors. And so it just makes the calculation garbage. And you really can't predict the weather, at least not more than like 5 days out. But anyways, it's an interesting topic. I will continue talking about this tomorrow in class. We'll talk about inverse matrices, and we'll also, if I have time, I'll try to show you how doing the Gaussian elimination algorithm is actually better for solving matrix vector equations than calculating inverses, because calculating a matrix inverse is really, really highly subject to this kind of round-off error that you get from double precision floating point. And so anytime you have a computer calculate a matrix inverse and then solve a matrix vector equation, not only does it increase the computation time by a lot, because calculating matrix inverse is really computationally heavy, but it also introduces more round-off error than Gaussian elimination does. But anyways, yeah. Thanks for coming to my talk. We'll see you guys tomorrow.